Okay, let's get going. I don't have any new announcements, but reminders of things that you already know. This homework that's due next Tuesday, and final project is also due next Tuesday, and there's a final exam next Friday. Um, I know there's a lot of discussion on all of these things on Piazza. Um, are there any questions that you would like to address right here?
Sorry, I'm just worried considering the last several weeks have been really hectic and I doubt that that's
Oh
going to
yeah,
die
and then
down anytime
the
soon.
exams were the midterms, right? They were graded, and there were a couple of regrade requests. I think all of them have been handled. If you feel like your regrade request was not handled, let me know. Send a message, and one of us will take a look at it. And based on the regrade request, I think a couple of people's scores changed. Uh, Nothing significant. Any questions? Yes.
Are you ready to press now close?
Yes. Other questions? Have people started the homework 5? How's it going?
Not too bad.
It should be somewhat similar in effort like the perceptron, right?
It's, for me at least, a lot of it is what I've already done for Perceptron, but just, change that one step, kind of like how we,
Yep.
change the update step.
And in fact, that's pretty much the main point here. This homework, even though we gave you a little bit longer, I think personally it's a little less work than your previous homeworks, because it builds on things that you've already done. On the other hand, the advantage of this homework is that if you implement your SVM, you can run it on the project data. You implement a logistic regression, you can run it on the project data. So for the price of one, you get to, in a sense. Yes. Yes, they are different things. They are different algorithms because the losses are different, which means the gradients are different, which means the actual steps that are happening are different. So they are different algorithms. Yeah. Other questions? Don't forget the final exam next Friday. Importantly, it's on Friday at 10:30. It's not at the same time on the same day as class. If you show up at noonish on Thursday, I don't know who'll be there. I won't. So make sure you get that time on your calendar. Okay, if there are no questions, we're going to continue our discussion of neural networks. That's going to be the topic for today and a good part of Thursday as well. In the last lecture, we saw what neural networks were. These are directed acyclic graphs consisting of nodes that are neurons. And a neuron is nothing but a function that takes a collection of inputs and applies some linear transformation to it, and then applies a nonlinearity to it. And that's the output of the neuron. So in this picture here, if we do not consider the inputs and the constant, we have 3 different neurons, Z1, Z2, and Y. So this is just a cartoon example of a neural network that I have that we saw at the end of the last lecture. And one of the other things we saw on last Thursday was the idea that neural networks are universal function approximators. So for any continuous function out there, there's a 2-layer neural network that can get arbitrarily close to it. Any discrete function can be, or any Boolean function can be perfectly represented by a 2-layer neural network with only threshold activations. Every neuron has an activation. It's a possibly nonlinear transformation that gets that gets applied to this dot product W transpose X plus a bias term, and then there's a nonlinearity. If you do not have a nonlinearity, that That's basically the activation function that takes the input and then passes it on. It's called the linear unit. In this picture here, I have two inputs, x1 and x2. And then we have this one that's a bias, that's a constant bias that goes to every both the z1 and z2. X1, and then the z's are, this forms the hidden layer. And then we have an output layer. We can have many such layers. So the primary thing we saw in the last lecture was what neural networks are. They're directed acyclic graphs that have these certain behaviors. What we did not see, and we also saw what kinds of functions they can express, basically anything. What we did not see in sufficient detail was how do you make predictions with this thing? I kind of rushed through it at the end, and I'll talk about that once again. And we did not see at all how training works. With how do you train these neural networks? We'll see that today. One thing that, with respect to training, one important point that I did mention was when we usually talk about training neural networks, we don't talk about training the architecture of the network, the layout of the graphs, the number of nodes, and such things. All of those architectural designs, the architecture is the connectivity of the graph, the size of each layer, the number of the activations on all these nodes. All of these things are usually treated as a design choice. You basically say that I have a 25-layer network. Each hidden layer has 500 neurons in between. All of the activations are rectified linear units. Rectified linear units are simply max of 0, comma, whatever input comes in. And then the output is a sigmoid. Maybe how did I come up with that choice? Because maybe I know something about the domain. One way or another, I have an architecture, and when we talk about learning, all we do is use data to figure out what the weights on all these connections are. So training a neural network is essentially finding all those weights. Okay, so that was a sort of a quick summary of what we saw last Thursday. Now we're going to look at how we make predictions with this object here. And there's a cartoon example here. We have a two-layer neural network. The input is two-dimensional. You have two x's, x1 and x2. There are two hidden units. So sometimes we also say the hidden layer is two-dimensional. And then they have an output, a single output. And I think I mentioned this in the last lecture, but I'll say it again. In this cartoon example, we'll assume that both of these have a sigmoid activation. Each of those take the input with the dot product take the input, apply a dot product with the corresponding weights, and then apply a sigmoid transformation. And the output is linear. What that means is linear is just a bit of a confusing name. It just means that there is no transformation to the input, to the input of that node. So how do you make predictions with this network? So to make predictions, of course, we need to know what the inputs are. So the notation I'm using here is any node whose values we know is going to be shaded. So currently we know the value of x2 because it's part of the input. We know the value of x1 because it's part of the input. And of course, we know the value of 1 because it's 1. So this is where the property that a neural network is a directed acyclic graph becomes important. These edges carry information from one node to another. So given the value of x1 and x2, we have all the inputs you need to calculate the value of z1. All the inputs of z1 are present. So you can calculate the value of z1. How do you calculate the value of z1? Well, there's x1 and x2. There are these weights along these edges. So this edge is w11h. This one is w21h. And so you take the dot product of the corresponding weights and the features, you add that constant term, or equivalently, you're multiplying 1 with that value to get this thing here. So one way or another, we get a certain number. Just a linear transformation of the input. And then we know that the activation function here is a sigmoid. So we apply the sigmoid transformation to that dot product, and that is the value of z1. So given x1 and x2, we can now compute the value of z1. And so I've shaded it blue. X1 and X2 also allows us to calculate the value of Z2, but importantly, at this point, we do not have all the information we need to calculate the value of Y, because we don't know the value of Z2. So first, before we get to Y, we need to calculate the value of Z2. So Z2 is another network, another neuron. It has its own weights, which are different from the weights of Z1. And you take the dot product of those weights with those with the inputs, in this case X1 and X2. Its activation function is sigmoid, so you have the sigmoid transformation applied to that dot product, and now we know the value of Z2. We always knew the value of 1, so I can shade that also. And now, finally, we have everything we need to calculate the value of Y. And Y is simply, remember, I assumed here that the Y unit is a linear unit, which means it does not have any activation. So you just take the dot product of the weights with the inputs to Y. The inputs to Y are Z1 and Z2. And so you calculate that and you're done. Now you have the output of the network. So the output of the network is simply to produce the output of the network, you go layer by layer. You first, given the inputs, you calculate whatever can be computed using that, and you keep going through all the way till you run out of units to compute. This can be done in a very systematic way. Essentially, this is like a certain ordering of the directed acyclic graph. All the input nodes get computed before computing the value. Sorry, before computing the value of any node, you need to have access to all its inputs. That's pretty much the entire idea. Any questions? Can you implement this? If I give you a directed acyclic graph, what you need to do is visit the graph one node at a time. First, you access from the inputs all the way to the output, and you make sure that if you need to access the value of Y, you first have Z1 and Z2. But to compute the value of Z1, you need to compute the value of X1 and X2. But hey, we already have those values. So you basically go from input to output. Any questions? Yes. It is exactly that. In fact, you need to lexicographically, or you need, sorry, topologically, you need to sort. You're visiting the nodes in topological order. Now, whether it's computationally feasible or meaningful or useful to sort it or not is questionable. It depends on how you represent the network. So it depends on your underlying data structure choices. Sometimes maybe you don't care to represent it that way. You can use the fact that, for example, your programming language might afford certain features that don't need you to sort it. You just recursively make the call, and you keep the language itself takes care of it, maybe. So it depends on your underlying language, but conceptually you're right. You visit the graph in topological order, and because the graph is directed, there is a single order. And because it's directed and acyclic, there is a single, not a single, but there is a few equivalent orders that are all correct. You could have calculated Z2 before you calculated Z1. You could have calculated Z1 before you calculate Z2. It doesn't matter which of those you do first. But you cannot calculate Y before you come to Z1 and Z2. Yes.
Is it possible for, a node in a hidden layer to potentially not be dependent on the values of certain inputs?
Yes. You could, in theory, you could have really complicated connectivity. I'll show you a cartoon example. Maybe there's a single node here. Let's say this is, I'm not going to draw circles. Let's say there's an X1 and X2 and X3. And maybe there's a Z1 that depends on these two. Maybe there's a Z2 that depends on these two. And then there's a Z3 that depends on these. And then the Y depends on, I'll draw the arrows here. I could do that. It's directed, it's acyclic. Before I calculate the value of y, I need the value of z3 and x2. Before I calculate the value of z3, I need z1 and z2. I can calculate z1, z2. So the ordering would be first you visit z1, then you visit z2, then you visit z3, and then you visit y. And this is just, I just made this up, but you could be very, very creative with how you construct these things, which is a good thing and a bad thing. It's a good thing because it gives you a lot of flexibility. It's a bad thing because suddenly the design space is massive. So how do you know what to do? Well, that's where we rely on almost like folk knowledge. If you're doing a problem, if you're working on a problem involving images, there's a lot of decades of work that shows that convolutional neural networks are the right thing to do. Don't ask me what a convolutional neural network is right now, but it's essentially a prefabricated block of things that sits on your input that has a well-defined interface, and you just put that in. So there are many such prefabricated blocks that exist, and those are the ones that have fancy names. Like what we just saw here is a multi-layer perceptron, and it's usually abbreviated as MLP. There are other prefabricated blocks like the convolutional neural network or a recurrent neural network, transformers, graph neural networks. These are all just named abstractions for certain connectivity patterns. And the good news is any decent neural network library will have these as just blocks that you can glue together, at which point designing the neural network architecture is, it almost feels like playing with Lego. You're just putting your blocks together and then, pressing the button. Questions? I would like to present this exact same thing in a slightly different terminology. Because if you keep track of each of these numbers, you're going to end up with possibly billions of them. And so it becomes a pain to keep track of all of these things. You have to use these weird addressing schemes that I have here, and it becomes annoying. Instead, what if I said this whole thing is a hidden layer, right? Z1 and Z2 is a hidden layer. Let me just give it a name. I'll call it Z. It's two things, two numbers. Two numbers arranged in a list is a vector. So Z could be a vector. X is another vector. Y is, in this case, it's just a number, but it could have been a vector. You could have been computing many such Ys. To go from X to Z, you're doing all these multiplications, right? Instead of doing that, you could put all of those, the weights on these edges, you can make it a matrix. And so that matrix sits here. And similarly, here there's a vector. I'm going to call it another WO. This is WH. You have a matrix, you have a vector. So rather than these kinds of diagrams, it's much easier to keep track of vectors and matrices as first-class citizens in your neural network library. A vector is an array of numbers. A matrix is a two-dimensional array of numbers. Who says you can have only two-dimensional array of numbers? Let's say we have a three-dimensional array of numbers. It's called a tensor. Any n-dimensional array of numbers is called a tensor, an array of arrays, if you will. So most neural network libraries essentially use tensors as the object that gets passed around. Layers are defined as tensors. The parameters are defined as tensors, and then there are all these essentially matrix vector products that the library takes care of underneath the hood. So I could have this vector X that represents, or a node X that represents a collection of neurons. It's really, in this case, it's 3 neurons. And X gets multiplied with this matrix here. And I'm sure you've all seen matrix vector multiplication. So I'm not going to belabor that. And it produces Z, but remember, Z is not simply the product of the weights and X, because you need to apply the activation. So you get the matrix vector product and then you apply all the activations, you get Z. And so I can compactly write that as Z is sigmoid applied to the weight matrix times the input. And the sigmoid is applied one element at a time. There are other activations that also take care of the interactions between them. Let's not get into that today. And then there's another vector here, WO, which then you multiply Z with WO and you get the final output. So the entire neural network can be defined in these two lines here. And what is really neat is I've written math here, but your PyTorch code does not look too different. There's a lot of scaffolding around it. There's a lot of junk that you need to write, but essentially your forward pass might just look like that. You have two sets of parameters, WO and WH, and given any input, you first multiply WH with the input, apply the sigmoid activation, and then you take that, multiply that with WO, you get a two-layer neural network. And of course, there's no activation there because we assumed that the output layer has no activation. If you want this kind of an object could be used for regression because the output's a real number. If you wanted classification, maybe you want to put a sigmoid here, just like we did for logistic regression. You get a binary classifier by slapping on a sigmoid there. Any questions? And once again, the forward pass works exactly the same way. I need to compute the value of y, but y depends on z, so I need to first calculate the value of z. But z depends on x. I know the value of x, so I can calculate z. Now I can calculate y. So it's called forward pass because information flows in the forward direction. Yes.
Why do people just call the n-dimensional, like, why do they start to call like n-dimensional?
Say that again.
Why do people start to call the n-dimensional array number as a
Why not just call it an n-dimensional array? Why give it a name? That's a very good question. I think there's a couple of reasons. There's a snarky answer to that, which I'm not going to give you. But I think one of the real reasons is once you start thinking of it as a tensor and not just some n-dimensional array of numbers, let's talk matrices. Why do you call it, why call it a matrix and why not just an array of numbers? Because if I have a matrix, then the idea of a matrix multiplying with a vector has a very specific thing, has a very specific algorithm. I can multiply matrices and matrices, and it's a well-defined algorithm. It's not like, you know how matrix multiplication works. It's not arbitrary products, right? With tensors, the generalization of matrix multiplication with a tensor is called a tensor contraction. That's also well-defined. So once you have that object, you can start defining algorithms on top of it and operations, and that specifies its behavior. And matrix vector product and matrix products are good examples of this. An array is just a collection of numbers. Why do we consider the concept of a vector and not an array? Because the minute you start thinking of it as a vector, we can start thinking of the geometry. The minute you start thinking of matrices, then you can start thinking of other things that you could do to matrices, like factorization, for example, SVD. With tensors, there are higher order versions of SVD that you could think about. So these sorts of operations open up. So it's technically speaking, it's just an array of numbers or an n-dimensional array of numbers. But because it's a tensor, it has certain behaviors. And those behaviors we can optimize in our low-level code. And those are the ones that are going to get used here, because this thing here where I put two W and X next to each other, you and I understand that that's a matrix getting multiplied with a vector, which means I need to go row by row and and such things. That's the thing. It's more than just an array of numbers. Other questions? The cleaner version of the same answer. The first thing um, is the first reason why we use tensors is because if we are going to keep track of every single node, every neuron in the neural network, it's going to get really ugly very quickly. So we want to treat it as we want to give names to collections of these numbers. But that still does not answer the question, why tensor? Why not just an array of numbers? The second thing is now we can write our code. We never write code talking that deals with individual neurons. We deal with these entire tensors. All the code that we write deals with that directly. Still does not answer why we need tensors. The third one is the more interesting one. We can use everything that we know from high performance computing and scientific computing for accelerating matrix operations to build neural networks. One of the big things that happened, I think I mentioned last week, how ImageNet became a big deal in 2011, where neural networks suddenly raised the state of the art by 10%. It turns out one of the big advances that that paper had that people did not recognize, in my opinion, sufficiently at that time, was that the authors of the paper were among the earlier users of GPUs for neural networks. At that time, GPUs were primarily for gaming. I think Alex K, I don't dare pronounce his last name, and Ilya Sutskever essentially wrote low-level GPU code so that they could train their neural networks. And that allowed them to scale things up. And GPUs allow you to do matrix vector products super fast. And the abstraction allows us to use the right set of tools. Also, this is one of the reasons why NVIDIA stock has been a sure buy for the last decade. Okay, other questions? Yes.
There could be one more reason, tensors have one more property that when you do linear transformations on tensors, it reduces the rank of the tensor.
That's an interesting comment. So I will I'll say it again in case you didn't hear it. Tensors have interesting properties. You can apply linear transformations to them. You can reduce their rank. You can play with their ranks. Except in neural networks, we don't do that. We don't use that property. We essentially, for the most part, treat them as collections of numbers. Almost. The rank stuff, I don't know if I should put Oliver on the hook. He's laughing because he was playing with that last year. And what you get from that is leaves a little to be desired. Would you agree? Yes. Okay. Was there another question? Yes.
Yes, what makes the GPU more optimized for doing major
Because you can do these things. There are many operations that you can trivially parallelize inside this, where you can have little parts of the matrix that you're multiplying sent to one compute core, and there are tens of thousands of them. So you can distribute this operation across the entire like tens of thousands of compute cores, each of them doing tiny bits of operation, tiny parts of matrix multiplication that are then getting reduced to at the sum. So this can be parallelized quite aggressively, and that's what helps. If you are interested in this kind of that question in more detail, I would encourage you to take one of the parallel processing classes, where they get into details of how do you do this with multi-core. The big difference between multi-core CPU versus GPU is with the GPU, you have tens of thousands of tiny processors. Whereas with multi-core, you have maybe, I don't know, 24 processors. So the scale is quite different. Communication between these processors can be very fast. You don't need to go to, there are a few. It's got to do with both communication of data between these low-level processors, and also to do with the ridiculous amount of parallelism that you get. In practice, when I've played with the same code being on a CPU or a GPU, I see orders of magnitude speed up when I go to the GPU. If you use it correctly. Good news is that things like tools like PyTorch abstract out most of that stuff from you. Not all of it, but almost all of it. So you don't ever have to think about this unless you want to kind of get into that level of open that door. Okay, that's all I have to say about the forward pass. The forward pass is very easy. There's nothing much to think about there. All you have to do is just compute a value before you compute before you compute a value, you need to make sure that all the inputs are available. So let's now talk about the backward pass, or an algorithm that's called backpropagation. We've seen what neural networks are. We've seen how to make predictions with it. And now we're going to look at the question of how do you train with a neural network, or how do you train the parameters of a neural network? The problem setup looks like all the other training settings that we've seen before. We have a collection of labeled examples. And we have a network architecture, which is the number of neurons, their connectivity, and all their activation. I would argue that when we were talking about perceptron or SVM or logistic regression, we also committed to a certain network architecture. The network, the quote unquote neural network for logistic regression, is nothing but you have some input, you multiply it with some vector W, and you get the output, and then you apply a sigmoid there. That one layer network is your logistic regression. So you committed to a certain network architecture, even for the simple linear classifiers that we've seen so far. Our goal is to learn the weights of this network. And a useful and important perspective here is that once the architecture of the network is frozen, the only thing that matters for the neural network that defines the behavior of a neural network with respect to an input X is all the parameters inside that network. Let's call all those parameters W. The weights. Sometimes you see theta. Now, the neural network's output is a function of the input and its weights. If I put the weights in the network and the input, I'm guaranteed the same output if I put the same weights in the same input. So the neural network is mathematically a function that's parameterized by its weights. So that's why I put W in as a parameter to this network. And this operation here, NN of X, W, is nothing but the forward pass. Given an input X, if the weights of the network were W, then I can apply the forward pass, I get an output Y. If I have a regression problem, the output Y is a number. Maybe I can do multiple numbers. If I have 4 outputs, I can have Y could be a vector of dimensionality 4. In fact, we don't talk about multi-class classification too much. Here's a 30-second lecture on multi-class classification. If you have K classes, your output dimensionality is K. And your final, every one of those classes gets a certain score. The label, the class that gets the highest score is the label, is the prediction. You can do a little bit more using an activation called softmax. And softmax is a function that has, if for the ith, so you have let's say you have y1, y2, and y3. You know what? I'll talk about softmax later. We'll not do this now. Anyway, I have a prediction. So far, this is just the setting. Another thing that we've seen a lot of is the idea of learning as minimizing loss. So we have a training set. So I have a classifier. I'm using the word classifier. You can also do this for regression. I have a classifier called NN that's completely parameterized by the weights. For every input xi in the training set, I apply the function NN of xi, w for a certain set of weights. That gives me my prediction. And then I can apply, we've seen loss functions before, so I can always, given the prediction and I can compare it to the ground truth. The loss function L is nothing but a function that penalizes the model for making a certain prediction when the ground truth is whatever value it is. That can be the loss for one example. Our goal is to minimize expected loss. As always, right? We want to minimize the expected loss on the true distribution of the data. We don't have access to the true distribution, so instead we'll minimize the empirical loss. We'll find a set of weights that minimizes the average, or equivalently, the sum of all the losses on the training data. So the goal of learning is to find a set of weights that minimizes the loss on the training data, and maybe you might want to throw in a regularizer to avoid overfitting. Usually with neural networks, we do not add a regularizer. We avoid overfitting using a different approach called dropout, which we'll talk about on Thursday. Anyway, so we have this. We've seen that this approach works for logistic regression, but you're deriving it for your homework right now. We've seen that it works for support vector machine. You're implementing that for your homework. We've seen that it works for perceptron. It works for least mean square regression. All of these are linear models. And do the same thing for non-linear models. We can do the same thing for neural networks. Any questions? In terms of our running example here, we have this neural network that we've seen, and given some example X, we can make a prediction Y. The loss takes the prediction, and let's say that the ground truth is some number Yi. Yi is the ground truth. It's a number because it's a regression task. And now, what is a reasonable loss for regression? If the problem you're solving is a regression, what kind of a loss would you use? Mean square error. Or in this case, we have just one example, just the squared error or the squared loss. So I can write down the loss is nothing but the difference from between y and yi, square it, we throw in a half because we're going to take a derivative eventually. Do you see anything interesting about this loss function? Oh, you know what? That's such a vague question. I'll tell you what's interesting about this loss function. The loss is a function of y and yi. Yi is of course fixed, right? It's the true label. We don't get to change the true label. But y is a prediction, so I can write down the loss as a function of y. The loss is a function of y. Importantly, loss is a differentiable function of y. The loss is a differentiable function of y, and the y is a differentiable function of all the weights. So the loss is a differentiable function of all the weights. So I can take the gradient of the loss with respect to any of those weights in this thing. So how do we solve this optimization problem, given what I just told you?
You have to take the gradient of the loss with respect to the weights.
Yes, and
Update the weights with stochastic gradient descent.
you could do that. There's a comment on Zoom saying gradient descent. You can use the gradient update. More correctly, more realistically, we could use stochastic gradient descent. We've seen stochastic gradient descent. You're implementing stochastic gradient descent. Let's see it for one more time this semester. You have a training set, and the inputs are some d-dimensional vectors. The label is something. It could be, if it's a number, it's regression. If it's a label, it's classification. You initialize all your parameters somehow, often randomly, and there are standard initializations that exist. And then you have to run for your learner for multiple epochs. After all the epochs are done, you return the final weights. In fact, you return the model with the final weights. You shuffle the training data, and then you iterate over all the training examples one at a time. Currently, let's say you're sitting on an example xi whose label is yi. You pretend that that example is the entire training data, and you compute the gradient of the loss with respect to the weights. Just as one example. And you take an update. So your weights are weights minus, you take an update in this direction opposite of the gradient. So if your gradient was this quantity there, you take an opposite step, so you take a negative there. And then there's a gamma t, which is the learning rate. How much does this gradient impact the weights? The learning rate, there are many, many tweaks that are possible, and I'll mention a few later on. Any questions about this? Yes.
Which weights would we take the grade with respect to?
All of them. Which weights did you take the gradient with respect to for logistic regression?
Yeah.
Why? What makes one layer special? You do it, it's a differentiable function of all the weights. You take the partial derivative of the loss with respect to all the weights. I'll show you a somewhat verbose version of this worked out in a bit. But basically, you take the gradient with respect to all the weights. And of course, you're going to be doing that by hand. No, you won't, because that'll, if just to kind of put this in context, there is a rumor that GPT-4o1 has 1 point something trillion weights. If anyone was computing gradients by hand, they would still be doing it. So clearly, we need some other solution. But before we go to the gradient, I just want to give an illustration of what this process might look like. Your loss landscape is no longer convex. You don't have this one basin that is the absolute global minimum, because your neural network is any neural network with more than one layer, usually with any reasonable activation in the middle layer, gives you non-convex loss functions. You might have multiple points that are local minima. One of them is going to be the global minimum, and our hope is to get to that, but in practice, we don't. Gradient-based optimization only takes you to a local minimum, and that's an important point. And I hope you can you know what this kind of a picture means, right? This is like a topological map of the valleys in the loss landscape. Each point here corresponds to one assignment to the weights. And when we are walking along this landscape, we are walking through a space of all possible models. Our goal is to get to the lowest point in this landscape. And before we talk about subgradient descent or stochastic gradient descent, I'll just show you what gradient descent might do. So for gradient descent, we still have to pick an initialization. So let's say we pick this point here. And let's say we pick that point randomly. At every step, you keep taking, you find out what is the direction in which the function grows the steepest and take a step in the opposite direction. At this point, the function is the loss over the entire data set. It's a giant summation. And you get this nice smooth path to the local minimum. If you start at a different place, you might end somewhere else. Right? So gradient descent could take you to different places depending on where you start. And some people use the metaphor of a ball rolling down a hill, and that metaphor has been very productive in kind of designing new kinds of algorithms that are variants of this gradient strategy. Let's see what stochastic gradient descent does. You still need to pick a random starting point, and let's say we pick the same starting point that we had before. In stochastic gradient descent, we are no longer guaranteed that the direction that you find for the gradient is a gradient of the full function. The full function is the sum of over all the data points. You're picking one example, and you're pretending that it represents the entire data. So the direction in which the gradient points may not be in the direction in which the function grows the steepest, which means that the step that you take, which is opposite of that, may not be directly pointing towards this valley. So maybe you take a stochastic gradient step, and this takes you on what looks like a drunk walk through this landscape. And eventually, the theory of stochastic gradient descent says, if you run this long enough, you will converge to the local minimum. You may take a lot more steps, but each step is incredibly lightweight because you're computing the gradient over just one example, or maybe a small set. We'll talk about that on Thursday. Each individual update is extremely inexpensive, so you can take many, many such steps very, very efficiently. This is just a sort of a cartoon illustration, a PowerPoint illustration of gradient descent. It's not even the right gradient. These are I just made up this red path. Yes.
So like in practice, does using stochastic gradient descent make more sense than?
In practice, we only use stochastic gradient descent. Actually, we don't use stochastic gradient descent. We use variants of that, but we only use stochastic gradients. The variants change based on how big the step should be, whether previous gradients matter for the next thing. Do you keep track of history and such things? But we still only use stochastic gradients because I'll give you one example. Once again, I want to use the example of a large language model. One of the largest public data sets that was used for training a large language model had, I think, 15 trillion tokens in it. It's public. Private data sets are probably bigger. I think, or 15 billion, sorry, 1.5 trillion tokens. And I think that's roughly, if you read a book a day, this corresponds to reading a book a day for, I did the math, some 100,000 years or something. So it's a large data set. And if you have to take a gradient, so for training a language model, you have to essentially do updates on this. If you have to do gradient descent as opposed to stochastic gradient descent, you have to go through the entire data set before making a single update. With stochastic gradient descent, you take a small subset of them, pretend that that's a representative of the whole thing, you make an update. And the cool thing is, most of these models are trained don't even have to look at the entire data before they stop training because of compute concerns, but also because you get good enough models before you even see the entire data. Other questions? So let's go back to this stochastic gradient descent. This is the entire algorithm. This is the biggest driver of progress in machine learning in the last maybe 2 decades. Have we solved everything? Can you implement it? In particular, we haven't talked at all about this question here. How do you compute the gradient of the loss with respect to the parameters? That's still non-trivial. Yes, the neural network is a differentiable function, and pretty much we only use differentiable functions except for the fringes of research, or maybe it's sub-differentiable. We should be able to compute sub-gradient. The actual value of the gradient and everything else depends on the choice of the activation, the loss function you use, and so on. This process was easy for SVM. It's easy for logistic regression. It's so easy that it's actually worth only 20 points in one homework in a machine learning class. Right? How do we find the subgradient of much, much more complicated functions? So you have hundreds of layers in computer vision models. You have billions of parameters in transformers. And if like I said before, there is no hope for computing gradients by hand. So we need an algorithm that can compute our gradients for us. This algorithm is called backpropagation. Backpropagation has been invented multiple times between the 70s to the mid 80s under different names. The final name that stuck was backpropagation, but it was not the first instance of that name. But just to keep stock of where we are, because we went through a whole bunch of different things. If we have a neural network, and that includes the architecture, which includes the structure of the graph, the activations, and the parameters, then for a new input, you can make a prediction. If you have the true label for that input, having made the prediction, you can compute the loss. If you can take the derivative of the loss with respect to each of the weights in the network, then you can use stochastic gradient descent. You can instantiate the gradient step. So the only thing that's left is how do you take the derivative of the loss? We're taking the derivative of the loss with respect to the weights, not the predictions, because the loss is the thing that we wish to minimize. Any questions about where we are? Now, for the next 25 minutes, I'm going to talk about something that you probably that might seem, at the beginning at least, it may seem ridiculously simple and familiar. Let's talk about derivative. I have a function, f, that takes two parameters, x and y. I can calculate the derivative of f with respect to x and the derivative of f with respect to y. So these are the partial derivatives. The partial derivative of f with respect to each of its arguments is 1. This should not be a shock to anyone. I hope so. Instead of sum, if I had a product, the partial derivative of f with respect to x is y. The partial derivative of f with respect to y is x. Right? Something that you may not always have seen before. If f of xy is max of x comma y, then we can't take partial derivatives. We need to take partial subderivatives. Here we have a subgradient. If x is the thing that maximizes this expression, then you take the gradient of x with respect to x, so it's 1. If x is not, so I can write it like this. F of x comma y is, it's either an x or a y. It's x if x greater than or equal to y. It's right. That means the partial derivative of this expression with respect to x is the derivative of this thing here with respect to x, which is 1 if x is greater than y. Otherwise, it's the derivative of this with respect to x, which is 0. So that's what I've written here. It's 1 if x is greater than y and 0 otherwise. The partial derivative of f with respect to y is 1 if y is greater than x. Otherwise, it's 0. At equality, you just pick one of those two things. I've written it a little bit loosely here. You put the equality only on one side. One useful thing to keep in mind is in all of these cases, what these derivatives represent is how much does this function change if the rate of change of that function, if the corresponding input is changed very slightly. It's a useful thing to keep in mind. We don't always use it, but it's good to keep this because it forms the basis of certain sanity checks that you can have in your code if you're implementing backpropagation. I don't want to have you implement backpropagation because we have only 1 week left. And if I give you a homework, I'm going to have a riot in my hands. But this is a fun algorithm to implement. You can think about how you do that offline. Let's take a more complicated function. Let's say I have three inputs, x, y, z. F of x, y, z is, let's say, x times y squared plus z. This is the kind of things that you might see in some calculus class. I have a function, I need to calculate the partial derivative of f with respect to x, partial derivative of f with respect to x. Can someone tell me what this is? Oh, no. Y squared, my z's and 2's look the same, and all my teachers throughout my education did not like me for that. But anyway, this is easy, right? You know how to do this. You can calculate all these derivatives by hand. Instead of doing that, let me make life a little bit more complicated so that we can actually go towards an algorithm. Let's say that I'm going to write down f as a product of two things, x and g, g, where g is y squared plus z. I could do that. So now I can calculate the partial derivative of f with respect to x is what? Using this notation. It's g, and the partial derivative of f with respect to g is x. I can also calculate the partial derivative of g with respect to y, which is 2y. The partial derivative of g with respect to z is 1. Nothing particularly complicated here. I'm just calculating a whole bunch of partial derivatives. The most important thing here that I've done is I have written this function as a combination of two simpler functions. One of them is nothing but this product that we saw before, right? We know the rule for the product. So I can calculate all of these partial derivatives. And at this point, the font size gets a little small. I hope this is visible. Okay. The key idea of backpropagation is that the function that you care about might be incredibly complicated, but you can break it down into these sorts of smaller functions, because if all I care about is the partial derivative of f with respect to x, y, and z, then I can write it this way. The partial derivative of f with respect to x is simply what we saw before, the value of g. That was the easy part. Let's now consider the partial derivative of f with respect to y. F is not directly a function of y. F is a function of x and g. But g is a function of y. So this can be written as the partial derivative of f with respect to g times the partial derivative of g with respect to y. This is the chain rule. That's the other big component here. And the partial derivative of f with respect to z, also we can apply the chain rule. Right? So given all the, so let's kind of recap here. I can take a complicated function and break it down into the composition of smaller functions. For each of these compositions, I can compute partial derivatives just locally. To compute this partial derivative, I don't really need to know anything about what g is. I just need to know that f is a product of x and g, so I can calculate this partial derivative, this one, without knowing what's happening with g. So all of these things are local operations. And then if I need the partial derivative of f with respect to any of the original inputs, I can apply the chain rule. The chain rule of calculus comes into play. So the key idea here is we can compute the derivatives of compound expressions by breaking them down into simpler pieces and then reassembling the derivatives that you want by carefully applying the chain rule. So far, so good? Okay. You said thumbs up. I'm taking you as a representative for the class. I don't know if the others, for someone else, it's not good. So we can do all of this. And I've just shown you an example that partial derivative of f with respect to y is actually 2xy, because it's x times 2y from there. And it turns out that it just comes because of the chain rule. I'm going to rewrite that expression slightly differently. I'm going to write this as something called a computation graph. A computation graph is how neural networks are internally represented inside any library. A computation graph is nothing but this graph of operations. So I have these inputs x, y, and z. Y and z together help me compute the value of g. X and g get multiplied to compute the value of f. So let's number these nodes. Let's call this 1 and 2. Node number 1 does not care what's happening to its output. All it knows is it gets these two inputs. This so happens that they are called y and z, but the names don't really matter. It gets these two inputs. I could call it left and right. It takes left, squares the value, and adds it to the value of right. And it computes a certain value, and it sends it out to whoever wants it. Node number 2 does not really care about who gives it its values. All it knows is any two numbers that comes in, it needs to multiply them. So just so happens that x and g show up, it multiplies them, and it produces the value of xg. But xg happens to be that function we care about because g was actually y squared plus z. This is a computation graph where every node knows how to compute a certain function of its inputs. And then these inputs are sent somewhere else. Does this seem familiar? This must look like a neural network. In fact, I could have introduced all of neural networks as computation graphs without actually going through this whole thing about activation functions and such things. The reason I chose to do it the other way is because that is the historical thing. I think there's some law somewhere that says that to teach neural networks, I need to have that diagram. For all practical purposes, I find it more useful to think of it as computational graphs, computation graphs. I can define forward pass using a computation graph. So if I know the values of x, y, and z, let's say x is 3, y is 2, and z is 1, forward pass is exactly the same as what we saw before. I need to calculate the value of f. To calculate the value of f, I need the value of x, I need the value of g. I don't have the value of g. So let me now calculate the value of g. I have all the inputs of g, so I can calculate the value of g. Its value is 5 because it's 2 squared plus 1. Now I have all the inputs I need for f, so I can calculate the value of f. F is 15. So I can systematically go through this graph to calculate the value. What I have just instantiated is the forward pass for this particular network. Okay? The backward pass computes the gradients, the derivatives of all the nodes. So having finished the forward pass, the backward pass always starts after the forward pass is done. Having finished the forward pass, now I can calculate the gradient of f with respect to x. But I know that f is a function that takes two arguments, let's call that left and right, and multiplies them. I can take the partial derivative of f with respect to L. L just so happens to be x. I can take the partial derivative of f with respect to R. R just happens to be g. The partial derivative of f with respect to x is exactly the value of g. In this case, it's 5. So the partial derivative of f with respect to x is 5. Why? Because this value was 5. I just copied it over here. Any questions about what just happened here? Now, I can also calculate the. Did you have a question?
Yeah, I don't know if it's jumpy ahead, but would you have like hard code in each one of these gradients?
Yes. All these small building blocks get hard-coded. Now, how many such building blocks exist? How many operators exist in mathematics? 100, 200, 500? Not infinite, right? But then using that vocabulary, you can build any function you want. That's the fun bit. And if you invent a new function that never existed before, it's your job to come up with a gradient. So I've calculated the partial derivative of f with respect to x. Now, the other side, I need to calculate the partial derivative of f with respect to g, which is, so if f was equal to xg, the partial derivative of f with respect to g is equal to x. But I know the value of x, so I can copy it over here. So now I have two partial derivatives, but that still doesn't give me the answer. What's the partial derivative of f with respect to the original inputs y and z? For that, I need to go one more step. The partial derivative of f, I know the partial derivative of g with respect to y. The partial derivative of f with respect to y is nothing but partial derivative of f. I'm going to just say derivative. From now on, partial derivative of seems very like a mouthful, but always assume it's partial derivative. So the derivative of f with respect to y is derivative of f with respect to g times derivative of g with respect to y. I know the value of, I know this value here, which was what I had already calculated. And I know this value because I know that g computes y square plus z. So I can, its partial derivative is just 2 times y. If y was 2, then 2y is 4. I multiply this partial derivative here is nothing but just for that edge, the partial derivative was 4, which is this quantity here. And 3 came from top, so I multiply 3 and 4, and I get 12. I can do the same thing for the other side. Importantly, when I'm calculating this particular partial derivative, I'm not going to recalculate this quantity. I'm just going to save it right there and read it off. The fact that the partial derivative of f with respect to g is 3 does not need to get recalculated every time because its number is not going to change in the middle of this process. So I might as well just save the number 3 here and read it off. That's the other big part of backpropagation. Don't do any work more than once. I think that's one of the biggest lessons in computer science, but I'll not talk about that right now. We can do the same thing on the other side. The derivative of f with respect to z, this should be a z. Z is derivative of f with respect to g times derivative of g with respect to z. This quantity here gets copied over from here. And the only new thing that needs to get calculated is the derivative of g with respect to z. And you get 3 here. Now we have all the partial derivatives we care about. What I have just walked you through is a forward pass and a backward pass. The backward pass is called backpropagation. The heart of all of this is a certain abstraction. Every node in this computation graph knows two things. It knows how to compute the value, its own value, provided the inputs are given to it. This is the forward pass. And it knows how to compute the partial derivative of the output, of its output, with respect to each of its input. So if I have a node here that multiplies left and right, on the forward side, it knows how to calculate the product. On the backward side, it knows how to calculate the partial derivative with respect to left and with respect to right. Every node in this abstraction knows these two things. These collections of nodes are part of your library. There is a node in the library called the product. Product is what I have there. There's a node that's the sum. There's a node called sigmoid. There's a node called dot product, which is built with products and sums. There's a node called rectified linear unit. There's a node called sine, cosine. Pick whatever mathematical functions you want. All of them have this property. You can build arbitrarily complicated functions using these sort of simple nodes that form your vocabulary by composing them. any continuous function can be built in this way. And that means that you should be able to calculate the values of the function by just forward pass. And then by repeatedly chaining the process backwards, you can calculate the derivatives with respect to any of the values, any of the inputs. So you get a process like this. Any questions about this? I haven't shown you backpropagation as an algorithm. I've kind of walked you through the process of backpropagation. I'm going to do that one more time. This time I'm going to do it for this neural network that we've already seen. Just to remind you of the notational convenience, we have I can represent entire layers as vectors and tensors. And sometimes we write down these sorts of things. We write down derivatives with respect to entire layers. It's just shorthand notation. The building blocks are, first one is the chain rule. If y is a function of z and z is a function of x, then y is of course a function of x. If these functions are all differentiable, then I can take their derivatives. The derivative of y with respect to x is nothing but the derivative of y with respect to z times the derivative of z with respect to x. Chain rule must be awfully familiar to you. Maybe this is the first lesson in calculus, I don't know. It also applies when you have more complicated shapes here. If y is some function of z1 plus another a function of z2, and z1 and z2 are both themselves function of x, you get a graph like this. So the derivative of y with respect to x is nothing but the derivative of y with respect to z1 times derivative of z1 with respect to x plus the derivative of y with respect to z2 times the derivative of z2 with respect to x. This is correct. And if you think about it, you'll see that this is correct. There's nothing special about the number 2 here. I can have many, many things. If y is a sum of functions, if y is a sum of these kinds of functions, then, and each of those functions are themselves functions of x, then y is a function of x. And so I can calculate the derivative of y with respect to x, which is simply the sum of these. So the partial derivative of y with respect to x is simply the sum of, in using the notation there, I could do it something like that. This is an important collection of building blocks. So now I can let me walk you through backpropagation, just like I did with the forward pass. I'm going to walk you through the backward pass for this neural network using all these pieces of information that we have. We want to calculate the derivative of the loss with respect to each of these weights. These weights define the neural network. Given the architecture, changing those weights changes the behavior of the function. I want to calculate the derivative of the loss with respect to all these weights. And to address your question from way back, all of them, not one layer at a time. Because L is a function of 9 things here. So let's go through this one at a time. If the forward pass proceeded in this direction, in what's called the topological order, the backward pass proceeds in the reverse topological order. It goes out like this, goes down like this. The loss is a function of the output here. So what I would like is to calculate the value of the derivative of the loss with respect to each of these weights. And importantly, all of those weights, the loss is a differentiable function of all those weights. So let's now go through this process. It's going to be a little bit tedious, but hopefully you'll appreciate your libraries a little bit more once we are done with this process. And in fact, like I said, it's a fun programming exercise to implement this. It involves a lot of bookkeeping, and there will be bugs with bookkeeping, and so it'll keep you busy for a few days. Um, it's that kind of fun. So let's calculate the partial derivative of the loss with respect to WO01. The loss is a function of y, and y is a function of the thing that that we would like to calculate the derivative with respect to. So we can apply the chain rule. The derivative of L with respect to the weight is the derivative of L with respect to y times the derivative of y with respect to that particular weight. And this is where the building blocks start kicking in. The loss is just a standard squared loss. I could be calculating the derivative of that by hand, but quite likely somebody has done it and put it in the library. So this quantity, the derivative of L with respect to y, is something that is part of the library, and it's simply y minus y star. So life is good. We don't need to implement it. That building block exists. The derivative of y with respect to this weight here is also part of the library. Well, in this case, it's pretty simple. It's the number 1. So we don't have to think too hard about it. So we've calculated the partial derivative of L with respect to that weight there. Let's do one more weight at the output layer. Okay, I want to calculate the partial derivative of L with respect to WO11. L is not directly a function of that, but L is a function of y, and y is a function of that weight. And so again, apply the chain rule. Partial derivative of L with respect to y is y minus y star. Partial derivative of y with respect to WO01 or 11, I guess, is the value z1. But importantly, we know the value of z1 because we've already finished the forward pass. If you finish the forward pass, we've calculated all these intermediate values. All you just have to do is make sure you don't erase that part of the memory. The other thing that's important here is when we calculated the partial derivative with respect to that weight, we had already calculated this value. In the spirit of never doing anything more than once, we don't have to actually recalculate that value. We just read it we just memorize it. You can cache it and read it from the cache. So that way you're saving some work. It seems like you're not saving a lot of work, but as we go down the chain, a whole amount of work gets, you don't need to do it because you've already done it before. So caching is the important point here. Backpropagation, at the heart of it, is chain rule with caching of intermediate derivatives. If you keep doing that again and again, then you have the backpropagation algorithm. In the 1 minute that's left, I'll just show you how this works for the partial derivative of L with respect to W22H. That's this weight here. L is clearly not a function of that directly. L is a function of y. Y is a function of Z2. Z2 is a function of the sigmoid. The value of the sigmoid is a function of that weight. So I can apply the chain rule systematically. So I want to calculate this partial derivative. I can say that the partial derivative of L with respect to W22 is with respect to y times the partial derivative of y with respect to W22. Partial derivative of y with respect to W22 is simply the partial derivative of this quantity. I'm just going to make life a little simpler. It's all of these things, but most of them get to 0. So really, you're just left with WO21 times the partial derivative of Z2 here. The partial derivative of Z2 with respect to that, well, Z2 is really, let's call this, it's a sigmoid of something. So I can say it's a partial derivative of Z2 with respect to the value of the sigmoid times the partial derivative of the sigmoid with respect to its input. We know what the partial derivative of a sigmoid is. I think I mentioned this when we talked about logistic regression. It's sigmoid times 1 minus sigmoid. And Each of these partial derivatives is easy. I'm kind of going through this a little bit faster than I would like because we are out of time. We'll pick up from here next week, but the most important point here is most of these quantities have already been computed for previous steps. And so really you'll be doing very little extra work for each new partial derivative we compute. And that's the key point of backpropagation. We'll stop here. On Thursday, I'm going to pick up from here, and then we'll talk about practical aspects of neural networks and caveats and such things.